In this video, we're going to talk about the solubility of a solute. These are your learning targets. In our previous video, we talked about a substance being soluble or insoluble. Remember what those two words mean? Soluble means that a solute can be dissolved in a solvent, whereas insoluble means that a solute cannot be dissolved in a solvent. And in this video, we are going to discuss the solubility of a solute, which is the maximum quantity of solute that can dissolve in a certain quantity of solvent at a specific temperature. So how do we know, first of all, that a solute can dissolve in a solvent, or which solutes can dissolve in a solvent? We are going to learn this general rule, like dissolves like. And again, this is a general solubility rule. It tells us that polar solvents can dissolve polar solutes. Polar solvents can also dissolve ionic compounds. And then nonpolar solvents dissolve nonpolar solutes. So we're going to review how to tell if a substance is polar or nonpolar. But again, just to reiterate, like dissolves like, the solute and solvent both have to be the same polarity. So both of the solute and solvent need to be nonpolar, or both the solute and solvent need to be polar or ionic. This is the reason why oil and water don't mix. Oil is nonpolar, whereas water is polar. This goes against the solubility rule, like dissolves like. So let's review these three words, ionic, polar, and nonpolar. First of all, what's the difference between these words? Well, polar and nonpolar substances are covalent molecules. So ionic compounds are made up of cations and anions, something that's positively charged and something that's negatively charged. For example, magnesium 2+ and nitrogen 3-. From that, we get magnesium nitride. Well, our covalent molecules, we would first draw out the Lewis dot structure, and if we see lone pairs, so remember lone pairs on a central atom, or different outside atoms, we know that we are dealing with a polar molecule, whereas nonpolar molecules have no lone pairs and they have the same outside atoms. Now, I could go into it, and we talked about polarity that has to do with electronegativity, right? But this here is just our simple test of if a molecule is polar or nonpolar. So just to review, when we talk about lone pairs, we're talking about, for example, like oxygen in the middle, and if we had chlorine on the outside, these lone pairs are on our central atom here. Okay. The different outside atoms would be if, for example, chlorine was something else, like fluorine. Those are different outside atoms. That would also tell us that it's a polar molecule. Whereas nonpolar, it has no lone pairs, and it has the same outside atoms. For example, methane. Okay. Methane has 1 carbon and 4 hydrogens, and no lone pairs, and same outside atoms. So let's discuss why polar solvents dissolve ionic compounds. Well, ionic compounds, we just talked about, consist of a cation and anion, which is positively charged and negatively charged. So if you take a look at this picture here, here's our positively charged cation and our negatively charged anion. Well, when it gets dissolved in, for example, water, because water is a polar molecule that we've known since biology. Well, polar, we know there's a partially positive side and a partially negative side, right? We didn't talk about this in our previous slide, but we did talk about it when we learned about polarity back in the unit when we talked about Lewis dot structures. So this has to do with electronegativity, and so what's going to happen here? Well, the partially positive side of our polar molecule, our covalent molecule, will be attracted to the negative negatively charged anion, okay? Or the negatively charged part of the covalent molecule will be attracted to the positively charged cation. And so if you look at this picture over here, you see that the cation is attracting all the partially negative sides of our solvent, right? And if you look here, there's the anion that's attracting the partially positive side of our solvent. So that's how polar solvents are able to dissolve ionic compounds. So let's take a look at this practice problem. Which of the following compounds will be able to dissolve in water? First, determine which ones are polar, ionic, and nonpolar. Now, the first thing you need to do is really draw Lewis dot structures for those molecules that are covalent, right? Ionic we know is ionic because it has a metal and a nonmetal. Covalent has everything nonmetals. And then once you figure that out, you're able to apply it to the general solubility rule, like dissolves like. So let's take a look at our solvent, water. Now, I know you know what it already looks like, but just for the sake of reviewing, I'm going to go ahead and use this to review. So if you look at water, the first thing we have to do is, once we realize that it's covalent, we need to add up our valence electrons, right? So we have one from hydrogen, and there's 2 hydrogens there, so it's times 2. Oxygen has 6 valence electrons, so 6 plus 2 is a total of 8. So the first thing we want to do is put our single atom into the middle. So we have oxygen in the middle, and then we are going to place the other atoms on the outside. So here we have 2 hydrogens, and we're going to make a bond between the outside atoms and the central atom, right? So each bond we have 2 electrons, so a total of 4 electrons, and I'm going to subtract that here. So we have a total of 4 that we're working with. So remember where these 4 go. Hydrogen doesn't want it because hydrogen wants a maximum of 2. So these 4 electrons are going to go right around the O. And that used up 4 electrons. We have no more to work with. Are they all satisfied? Yes, hydrogen is satisfied with 2. Oxygen here has 8. So there is our Lewis dot structure. So is this polar or nonpolar? Polar because of the lone pairs. So we said water is polar. So now let's take a look at our solutes. First one is sodium chloride. Well, I hope you're not drawing this as a Lewis dot structure because we first recognize that sodium is a metal and chlorine is a nonmetal, so that tells us that this is ionic. What about CCl4, carbon tetrachloride? Well, this is not a metal, so we know that it's covalent. So you would draw out the Lewis dot structure. And assuming that you're drawing it out right now, that you're pausing the video and drawing it out, you would find that carbon tetrachloride is nonpolar. What about ammonia, NH3? Again, another covalent molecule. You're going to go ahead and draw out the Lewis dot structure, and we see that ammonia is polar because the lone pair is on nitrogen. What about magnesium fluoride? Magnesium is a metal. Therefore, this compound here is ionic. What about the last one, carbon dioxide? Carbon dioxide is a nonpolar molecule. Okay, so we figured out that our solvent is polar, and our solutes, we figured out ionic, nonpolar, or polar. So which ones will be soluble in water? So now we want to go back to our general rule, like dissolves like. So remember, if our solvent is polar, what can polar solvents dissolve? Polar solvents can dissolve polar solutes, and it can dissolve ionic compounds, okay? So if we take a look at the first one, can sodium chloride dissolve in water? Yes, it can. Polar solvents will dissolve anything ionic. Will carbon tetrachloride dissolve in water? No, because one is nonpolar and the other one is polar. Will ammonia dissolve in water? Yes, it will. Will magnesium fluoride dissolve in water? Yes, it will. Will carbon dioxide dissolve in water? No, it will not. Next, we're going to talk about the 3 factors that affect solubility. So we're talking about how do we know how much solute can be dissolved in a given solvent. The first factor is that it's just the nature of the solute and solvent. So in this example, I talk about lead 2 chloride and zinc chloride. And if I have 100 milliliters of water and I try to dissolve lead 2 chloride in that, I can only dissolve 1 gram. Whereas if I were to try to dissolve zinc chloride in that, I can dissolve 200 grams of it. Again, it's just the nature of the solute. The second factor that affects solubility is temperature. Generally, an increase in the temperature of the solution increases the solubility of a solid solute. For example, let's say you have 5 grams of salt and you try to dissolve that in ice cold water. How much of that do you think will actually dissolve? Not a lot. You'll probably see a lot of the salt just dropping down to the bottom of your cup. But what if we heat it up? Then all of it will probably dissolve as we heat up the temperature. For gases, however, solubility decreases as the temperature of the solution increases. So think about a soda can that you left in your car in the middle of the summer. So let's pretend it's 100 degrees Fahrenheit outside. Well, what's going to happen after you find it about 2 days later? Well, if you said that the soda can is going to explode, you're incorrect. It's actually going to go flat. So what happened? When the temperature goes up, the gas is actually escaping from the liquid, or it's escaping from the solution. So that's the reason why your soda can goes flat, and that's the reason why we want soda in a fridge. The third factor that affects solubility is pressure. Well, think about when we talked about pressure. The only time we really talked about pressure was with gases, and that's exactly what it affects. For solids and liquids, if we were to change the pressure, it really has no effect on it. But for gas solutes, if you want to mix a gas into a liquid, for example, you want to increase the pressure, and that's actually how soda is made, right? And then a decrease in pressure decreases the solubility. So, like for example, soda, you're mixing gas into the liquid, and so you want to do it in lots of pressure. So, to sum it up, for most substances, solubility increases as temperature increases. In solutions involving liquids and solids, typically more solute can be dissolved at higher temperatures. This does not hold true for gases. For most gases, the solubility decreases as temperature increases. And this is what we're going to look at when we look at a solubility curve. So if you look at the solubility curve, a couple things I want to point out before we get started. On the Y, we have grams of solute, and then dash 100 grams of water. So this is telling us how much solute can be dissolved in 100 milliliters of water. So 100 grams of water is the same thing as 100 milliliters of water because the density of water is 1 gram per milliliter. And then on the X, we have temperature in degrees Celsius. So for example, if I look at KClO3, which is my bottom graph here, and it kind of looks like a spider web, right? Because it's showing you different substances. And let's say, for example, I want to look at how much I can dissolve at 40 degrees. Well, I find 40 degrees, I carry it up to my graph, and once it hits my curve, from there I'm going to read it on my y-axis, and that's about 15 grams. I can dissolve 15 grams of KClO3 when it's at 40 degrees Celsius. So that's how you read this graph. So let's take a look at some examples. What mass of solute will dissolve in 100 grams of water at the following temperatures? So for potassium nitrate, at 70 degrees, we want to find potassium nitrate, so here it is. And at 70 degrees, it's down here, and you want to take it up on the graph until you hit the curve, and then you take it along the Y as straight as you can, and that's about probably 125 grams. You do the same thing for sodium chloride, except this time I'm asking at 100 degrees. So here's sodium chloride at 100 degrees Celsius, and you take it up, and that's about 40 grams. Ammonium chloride at 90 degrees. Ammonium chloride is right here at 90 degrees, right here. So that's about 65 grams. Out of these three, determine which of the above substances is most soluble in water at 15 degrees. So at 15 degrees, which is right around here, it's asking me which one of these is the most soluble, meaning which one can I dissolve the most. So here's sodium chloride at 15 degrees. I can dissolve about 37 grams, would you say? Ammonium chloride, I can dissolve right around 29 grams. And potassium nitrate, I can dissolve right around 16 grams. So out of these three, which one is the most soluble? Well, that's sodium chloride. That I can dissolve the most, 38 grams. Again, it's asking out of these three substances here. Let's take a look at our example problems, or practice problems. At 80 degrees, the Hulk dissolved 50 grams of ammonium chloride in 100 grams of water. Did he make a solution that is unsaturated, saturated, or supersaturated? So remember what these three words mean. Unsaturated means that you can dissolve more, right? It doesn't contain the maximum amount of solute dissolved. Saturated does contain the maximum amount of solute dissolved in a particular temperature. Supersaturated means there's too much dissolved. So let's find ammonium chloride and let's find 80 degrees. Here's ammonium chloride at 80 degrees and we're right around here. So that's probably 60 grams? That can be dissolved at 80 degrees. So the Hulk dissolved 50 grams. That means he dissolved this much right here. You see how it's below the curve? Well, the curve tells us a saturated solution. That's the maximum amount that can be dissolved. So 60 grams can be dissolved at 80 degrees, while Hulk only dissolved 50 grams. So that means he has an unsaturated solution. What if it dissolves 70 grams at the same temperature? So instead of 50, now he dissolves 70 grams. You see how that's above the line? He could only dissolve 60 grams, but he dissolved 70 grams. So what do you think that means? That means he made a supersaturated solution. I'll show you a supersaturated solution. So this here, what this person did was he boiled the solution and he dissolved as much as he could. And then he cooled it down. So think about it. When he boiled it at a higher temperature, he was able to dissolve a lot more, right? And at that point, at that temperature, it was saturated solution. But then when he cooled it down, now at a cooler temperature, this solution is holding a lot more solute than it can hold, right? So look at what's going to happen when he adds one tiny crystal from that scopula into the flask. So again, this is supersaturated, and look at what happens there. Isn't that cool? You see the crystals forming in there. And there's your supersaturated solution when it's cooled down. Okay, back to our practice problems. How could Hulk make a saturated solution at 100 degrees? Well, at 100 degrees, he can dissolve about 72 grams in how much water? In 100 grams, or you could say 100 milliliters of water. Example 2. Which salt is least soluble in water at 20 degrees? Well, let's find 20 degrees. And out of all these salts that are shown in the graph, which one is the least soluble? Well, it's the one that we hit first, right? The lowest one, the lowest curve. We can only dissolve about, 8 grams, whereas everything else we can dissolve a lot more. So that one would be the least soluble, KClO4. How many grams of potassium chloride can be dissolved in 100 grams of water at 80 degrees? Well, where's potassium chloride? KCl, there it is. At 80 degrees, we can dissolve about 50 grams. At 40 degrees, how much potassium nitrate can be dissolved in 200 grams of water? So here's potassium nitrate. At 40 degrees, we can dissolve about, 42 grams. But what do you notice about this question? This is asking about 200 grams of water, not 100 grams of water. So what did I do to the water? I doubled it, right? So what do you think I'm going to do to the solute that can be dissolved? I'm also going to double it. So if we are saying that that's about 42 grams, so then 42 times 2, we have about 84 grams. Number 5, which salt shows the least change in solubility from 0 to 100 degrees? Well, look at all of these. Which one is showing the least change? Right there. That's salt right there, sodium chloride. A saturated solution of potassium chloride is formed from 100 grams of water. So potassium chloride is right here. If the saturated solution is cooled from 80 degrees to 50 degrees, how many grams of solid are formed? So at 80 degrees, you could dissolve about 40 grams. But at 50 degrees, you can only dissolve about 20 grams, right? So just like how I showed you on the video, that's going to fall out of your solution. So how do we do this? It's really just 40 minus 20 and you get 20 grams. 40 grams here, 20 grams here, subtract them and you get 20 grams. Number 7, how many grams of sodium nitrate can be dissolved in 50 grams of water at 50 degrees? Here is sodium nitrate, 50 degrees, right around here. So that's about 112, yeah? Except now, what did I do to the water? I only gave you half the water, right? So then what are you going to do with this problem? 112 divided by 2, and we get 56 grams. Why does ammonia decrease in solubility from 0 degrees to 100 degrees? So if you look here, we only have one curve that's going down, is going against everything else, right? Everything else you see is increasing except for NH3, ammonia. And why is this the case? What do we say about which substances will decrease in solubility as you increase the temperature? Only gases will, right? So this is telling us that ammonia is a gas. That's it for the solubility of a solute.